Thank you very much, Jean-Claude, for the nice introduction. So the Bauhaus University Weimar is located in Germany, not Austria. That's a small correction. I hope my voice is clear. I will start this webinar to present about the seismic performance assessment of cultural heritage buildings using Diana. The focus of this webinar is on unreinforced masonry structures, nonlinear modeling, or the techniques or the material models that are available in the software that can be implemented for analyzing cultural heritage buildings, particularly unreinforced masonry. We will talk a little bit about finite element model updating, the interpretation of structural response through linear and nonlinear analysis methods. And I will present a very preliminary analysis of two case studies located in Croatia, the Jesuit College in Dubrovnik and the Trakošćan Castle in northern Croatia, which are both cultural heritage buildings of UNESCO World Heritage List. So since around 1990, a significant portion of global natural disaster fatalities have resulted from earthquakes. Now, approximately 60% of these casualties are attributed to the failure of masonry buildings. And this is particularly important because if you look at Europe, then half or most of the European cultural heritage buildings are unreinforced masonry buildings made from stone or from clay bricks, but laid in very weak lime mortar most of the cases. This makes the structure extremely weak in terms of strength to lateral motions, where the structures exhibit very low tensile capacity. The cracking response is very brittle, and the structure shows very limited ductility in the nonlinear range. Now, part of the problem also is because cultural heritage buildings are extremely old. There are oftentimes retrofitting or modifications that are done to the structural system, which are less helpful than and causes even more problems, or localized damage cases solves one problem but causes many other issues in the overall structural response. And the buildings, because they have stood for a very long time, they suffer from environmental degradation, has a very heavy weight, and irregular geometrical openings, which causes stress redistribution to areas where you don't want these stresses to go to. A part of the problem also is in the inadequate connections of the walls to the floors, so from the wall-to-wall connections. And all of this combined together makes these buildings extremely vulnerable in case, or particularly in the case of seismic action or lateral motion. Now, when we deal with cultural heritage buildings, we do not typically start with a complete set of information. So the data is very scattered, the technical documentation is often unavailable, the ownership of data is very fragmented, and in many historic archives, the data is not even digitized. So from collection of data to the geometrical complexity and then to the material composition, as you can see from the image here, the material is not very consistent. For example, in this case, you would see here that bricks that are laid in a pattern where the head joint is visible, and here you would see where the bed joint is visible. So the bricks are not laid in a uniform fashion, and then you see they are connected to different type of elements. For example, in this case, we have a dressed stone. In this case, we have an irregular stone. So when a wall is made from such a complex combination of different types of material laid together, then forming a continuum model out of this becomes a very complex case that we typically deal with. So characterizing such type of masonry where data is very unavailable or where you cannot make material tests because of the cultural integrity of the buildings, it becomes very complex to model the nonlinear material response in a realistic or in a certain manner. The problem also is between the connections and how to deal with these connections in a realistic way. For example, in this case, you would see that the floor is connected to the walls, but the connection is rather uncertain. So if you really look into it, you would assume that there is no connection between the wall and the floor. And in that case, the damages to the wall comes mostly in the out of plane direction, which can only be resisted through proper connection with the floor system, and they are sometimes very difficult to analyze because the out of plane mechanism is very localized in nature. Now, the previous retrofitting strategies are sometimes also problematic to consider in numerical models. For example, in this case, we have a tie rod where the strength of the tie rod is rather unknown. The pre-stressing force which is applied to the tie rod is also unknown, and how this tie rod is connected externally using plates or rods to the outside of the wall is also something which is difficult to determine on how that connection is and how much stress transfer is going on between the wall and the tie rod. Now, regarding the digitization of the drawings, if you look at the one of the drawings here, which comes from the Institute of Art History in Dubrovnik, you would see we have a dome-shaped structure here, and then this dome-shaped structure is connected to structural walls where the openings are even not regular from the inside to the outside. You see the inside opening has a larger size than the outside. This brings geometrical difficulties in your structural models or make the mesh of the structure more complex when you model such type of peculiarities in the structural system. And this brings us to the point where we have to consider on how detailed the structural model should be and what are the peculiarities that you do want to consider in the structural model, and what is the information that can be excluded from the structural system. One particular aspect that cannot be excluded is how the connections are formed between wall to wall, between wall to floor, and between different structural components with the walls. But this is something which is extremely difficult to model because these connections are largely unknown, and assuming a property for the interface rather leads to uncertainties than making the analysis any better. So we have to be very careful when modeling connecting parts with each other in the software. And I will later show you why we exclude them in the numerical model in certain cases where we don't know anything about the connections. It's rather better to exclude them than to consider them and have weaker structural response in a particular direction or stress concentration near the edges of the walls. Now, when we have a geometrical model and when we do not know the material properties, then to ensure that the structural model represents the response of the actual structural system, the methodology that we adopt is called finite element model updating. So we create an initial model or an initial geometrical model, and we assume the material properties according to what we see or visually see from the pictures or from the archive or drawings. So visually, if the material looks like it is stone, then from books and from different references which corresponds to the particular area of interest. For example, in this case, it's Croatia. So I'm going to pick material properties which are most relevant or closely relevant to the case study that is in question. In this case, in Croatia, for example. Once you pick the material properties, you do not pick specific material properties, rather you pick a range of material properties. So you say that If I have stone masonry, I can go from an elastic modulus ranging from this value to that value. So you always have a lower bound and an upper bound value to play within. Now, once you have a geometrical model and you have a preliminary set of material data, our next step is to go and to run an ambient vibration test on site to determine the frequencies or the fundamental frequencies of the structural system in question. Now, when we run the ambient vibration testing, we identify the fundamental modes, or we identify the frequencies corresponding to the fundamental modes of vibrations of a particular structure. We can now run modal analysis in the software, in this case Diana, for example, and always compare our values of frequencies from the numerical model to the experimental case. Now, every time you compare the values, you would see a particular error. Now you can look at this graph. We are comparing two frequencies in two different directions between the numerical model and the frequencies that are observed or that are determined on site in the field. Now, for the first run, where we have a particular material model, you would notice that the error, for example, in one of the frequencies is around 20%, and in the other direction or in the other frequency for the same material, the error is around 5% or 6%. Now, this means that for one direction of analysis, maybe the material property represents the actual structural system, but for the other direction, it does not. And I need to find a material property which is neither this or that. I'm trying to find something in between, or a material or a composite that can represent the structural response in all directions of the structural system, or the dynamic response in all directions. And to do this, we change the material properties now in the ranges that we took from the literature, for example. So we are changing now the elastic modulus, we are changing the Poisson ratio, we are changing the shear modulus. And by doing this, we are constantly observing that the error keeps changing between different frequencies. And you would see sometimes they come very close to each other. Now, depending on what you are analyzing and how much error you can allow in the dynamic response, you say that, okay, I pick either this set of material properties or this set of material properties or this set of material properties where the error is minimum, and I use these material properties for any further analysis. But because you are based on a particular information of error, and because it is only because you are comparing everything with an eigenvalue analysis, everything that you are doing at this point is in the linear elastic domain. That means that all the nonlinear properties that you consider later on has nothing to do with the finite element model updating, and those properties might or might not represent the nonlinearity of the actual structural system. And for this reason, we do not run only one analysis to get the structural or the seismic response. Rather, we always choose a set of material properties which leads to the minimum error that can be used to derive a subset of results. So we have always a bandwidth of results that we are working with. Because the material is uncertain and because we are not sure which one of this set of material actually represents the actual structural system. Now, regarding the material model, there are options in Diana that can be used. For example, we have the engineering masonry model, which can be applied to shell elements. And in this case, we cannot do that because typically in cultural heritage buildings, the walls are of irregular shape, which means the cross-section is not consistent along the length of the wall. And to use a shell element with a particular geometrical cross-section is not really possible. So in this case, when you have irregularities and when you have structural system which cannot be modeled with shell elements, then a good choice of material model is the total strain crack model. Now, there is a lot of information about this already, and there are so many studies which have calibrated the model and validated the model for regular and irregular geometries for different type of masonries. But I will give you a brief introduction to what is possible, what do we use, and how do we use it. So the total strain-based crack model, it was originally developed along the lines of the modified compression field theory, and this was later extended to 3 dimensions by Selby and Bichiro in 1993. Now, the model is a smeared crack approach, and it typically means that the continuum, the stress is evaluated in the directions given by the principal crack orientation. Now, the stress in this case is defined hypoelasticity, with hypoelasticity where the loading and unloading behavior is along the same stress strain path. But the user manual for Diana says that in the current version, the behavior in loading and unloading is modeled differently with secant unloading, which you can see here, and it's controlled by the factor alpha. Now, there are many possibilities that you can choose from, for example, the ones that are marked here in the red box, and it becomes sometimes very difficult for a practicing engineer to understand and to determine which of this property should be chosen in a practical case scenario where you want to make a preliminary analysis just to understand how the structure behaves generally without going into local mechanisms or local crack orientation, or without going too much into the details of how the cracks propagate from one point to the other. Now, I will briefly explain them one by one to give you an idea on what we choose and why do we choose them. So the stress strain relationship can be fixed or rotating or coaxially rotating. In the fixed case concept, the stress strain relationship are evaluated in a fixed coordinate system which is fixed upon cracking. So once a crack is formed, the orientation of the crack is fixed, and then everything else, or the nonlinear response, is determined on the basis of this fixed orientation. In the rotating crack model, the stress strain is evaluated in the principal direction of the strain vector. Now, oftentimes, what we observe in numerical analysis is that with the fixed crack orientation concept, we typically see that there is a stress locking, and which leads to a little bit overestimation of the strength, capacity, and the ductility of the structural system. So when you are dealing with material models that are highly unknown, or where you don't know the material properties, and you want to make a global analysis without looking into the local mechanisms, or too much without looking into the propagation or too much detail of the propagation of crack, it is always a better idea to go with the rotating crack concept, because then you are underestimating capacity rather than overestimating capacity. Now, for the tensile behavior and the compression behavior, the stress strain relationship can have many options. Which option is the best option is rather unknown, and you can choose from a variety of these options. That's why I said you can form a structural model by choosing, for example, fixed here and then rods here and then no reduction here. But you can also choose fixed with Govinji and no reduction, or you can choose rotating with rods and no reduction. So the variety can be huge. And when the variety can be huge, then the uncertainty that arises from the choice of your material model becomes also extremely large. So the results for various assumptions can show large discrepancies. So smeared crack may give rise to locking, and the fixed smeared crack may produce overstick behavior, while rotating smeared cracks do not. And in this case, choosing what is right and what is wrong rather becomes very ambiguous and difficult. That's why we evaluate the structural system on the basis of the worst possible response. And the worst possible response means that you evaluate the structure on the basis of not only one set of material and not one set of material configuration. You evaluate the structure on many sets of material and on many sets of material configuration. This gives you a whole large range of structural response, which you can use to evaluate or globally evaluate the structure in a rather preliminary way. Now, to understand this, I would suggest a webinar from Dr. Francesco Parisi about the benchmarking of different modeling approaches to simulate the seismic response of URM structures, or you can read the report written by Professor Ross on the crack models for concrete. And these will help you understand a little bit on what does each of this option rather mean, and how you can evaluate later on if you are working with a localized model or you are working with a model where it becomes necessary to know the orientations of the crack or to know where the structure is damaged and how it is damaged. In this case, because we are dealing with a preliminary analysis, it is not necessary to really differentiate between different options. Rather, we are looking for a preliminary analysis to understand the global response of the structural system. But the choice, just to emphasize on the point, the choice that you make here affects the nonlinear response rather in a very diverse way. Now, from the analysis and output point of view, in seismic analysis, it is possible to run a static analysis with different load combinations, and these load combinations can originate from different seismic codes. In this case, I use the seismic codes, typically the Eurocode 8. You see the equation on how the load combination works. You have the dead load with a factor, and then you have applied loads in the structure, pre-stressing loads or dead applied loads, and then you have the live load with the earthquake load. We also, when we are dealing with irregular geometries, then we try not to do the performance assessment on the basis only of static analysis. Rather, we also do or deal with the dynamic analysis, because the dynamic response of the structure in this case becomes very relevant. Now, in the linear domain, this can be done with the response spectrum analysis. Diana gives you the option to run a free vibration eigenvalue analysis. The modal combination and the load combination both can be combined. We use typically the CQC or complete quadratic combination. Because we have high irregularities, SRSS, so the modes are typically closed. SRSS, or square root sum of the squares, is not the most ideal way. And then you can superimpose these results with static load combinations later on in the output of the response spectrum analysis. What is missing at the moment is we cannot run a rich vector analysis, which is sometimes very helpful in cultural heritage building, because you are dealing with large masses, and to simulate or to activate these masses in a particular direction becomes extremely difficult. Now, we also deal with time history analysis when it is required and we are interested in nonlinear response. We can combine the time history records in orthogonal directions outside of the load combination. So if you want to combine two horizontal components from a seismic station in one particular analysis, then you must define these time-dependent factors outside of the load combination and rather with the loads. If you define a load, if you define the time-dependent factors or the time history record in the load combination, then unfortunately you cannot combine them in a one or a single analysis. Now, some of the useful output that I typically look at when dealing with a preliminary analysis is to look at the global deformations, because they help you understand where the most of deflections in the structural system are. We also look to the global forces, particularly in the nonlinear analysis or a pushover analysis, to determine the base shear forces. Principal stresses are also extremely helpful when you are looking for stress concentrations or when you are looking for stresses that originate and that propagate in a particular direction. We also look to global stresses because they help you somehow understand the in-plane and the out-of-plane shear response. Although I must mention here that you cannot compare it to the shear stress limits of the material because they are shear stresses in the presence of normal stresses. So they are not principal stresses, and this must be carefully interpreted later on when you are dealing with the results. It is also helpful to look to the principal and the global strains in a particular direction, because then the stresses sometimes gives you a larger view or a very broad perspective of or a very large distribution over the facade or the wall. But the principal strains or the global strains, they help you understand things on a deeper level or in a much localized way. That you will see later on in some of the results. Now, this was a general introduction on how we deal with the subject. Now I will present the first case study. The Jesuit College is an 18th century stone masonry structure which is located in the historic center of Dubrovnik. Now the structure is made of masonry walls in very weak lime mortar, and has vaulted floors with timber diaphragms and then very irregular wall thickness. Now, during the Montenegro earthquake of 1979, the building experienced facade cracking and local interior damage, although we have no images of this, but this is what is reported in the literature very widely. Now, the seismic hazard map indicates a ground acceleration of 0.25 G for a 475-year return period at the site. And this is what we will use as an information for our response spectrum analysis. Now, the model is constructed geometrically using the information from the structural drawings like this. For example, we have very complex vaulted structures where we have cross walls, sometimes we have barrel walls, and sometimes we have different cross walls coming into the corridor connected with different directions in a very complex way, such as like this, for example. The material is very diverse, which means that bringing this into a continuum brings a lot of uncertainties, and we must not work with one material set. Rather, we will work with a large set of material data that will give us a large set of results which can be used, or the worst case scenario can be used to identify problematic areas in the structural system. The connections in these cases are unknown, which is why we will not model the connections particularly. Rather, we will assume that we have a good connection, but later on, if this goes into the retrofitting campaign, then we investigate the connections to identify the proper connectivity of different structural components, and then update the model and rerun the analysis for a more detailed seismic assessment. Now, in this case, we use the total strain-based crack model. The crack orientation is rotating because we do not want to overestimate the capacity. The crack bandwidth is based on the principle of rots, and the Poisson effect after cracking is based on damage. The tensile behavior is modeled in this case with the exponential law. Of course, there are options that you can choose, or other options that can be used. We do use the other options as well for this particular analysis. In this particular case, we are using this, but this is just one subset of a very large database of results. So we use other models to derive other results, and then out of all these results, we derive the weaker or the most damaging case as the representative case. The compressive behavior is modeled with the Thornfeld law, which looks like this. And the compressive behavior has no lateral confinement, so there is no increase because of lateral confinement in this particular case. The mesh is variable in size depending on how small a structural member is. We do run a mesh sensitivity analysis to see that the results are somehow reliable, or that what we see in terms of stresses makes sense. But a good way to estimate this is to define the goal or the objective of the analysis in the beginning. If you are running an analysis where you want to see a particular damage pattern, then you must run with a much finer mesh size, because that helps you see the propagation of stresses in a particular direction. But because most of the time we want to run something really quick, and we do not want to have a very detailed mesh, then the reliability of the results can be a good estimate of how fine this mesh should be. So the time that it takes and the detail of the results that you want determines on how refined this mesh should be. Now, in this case, we went to the site and we monitored the building response in 2 orthogonal directions using the instruments that look like this. Now, we took many set of measurements, and they are all ambient vibration testing instruments. So we took many sets of measurements at these locations. Each of the set was about 20 minutes long. We only had one instrument at the base here, which monitored the display, which monitored the dynamic response or the accelerations over 3 days. So it was a rather a long-term measurement to have consistency in the wave or in the acceleration that we were getting from the instrument. Now, out of all these vibration recordings, we derive something that looks like this. So we identify the fundamental frequencies of the structure because we have measurements in 2 orthogonal directions. We try to identify the peak frequency that we observe in the north-south direction and the east-west direction. And once we have these 2 frequencies, we go back to our numerical model. We change the material properties in increments, and we run the analysis. And now we are observing the error between the observed frequencies and the experimental numerical frequencies. And once we see that the error is reduced, then we come back and we look to the mode shapes, and we see that the modal response for these frequencies should look or looks like that. What you see here in the first mode is the frequency that we do not see on the experimental campaign, because it is a local frequency of just this clock tower from the external facade or from the front facade of the building. But what you see in mode 2 and 3 is the frequencies which correlates to the frequencies that you see from the experiment or from the actual site. And this gives you the information on how these frequencies from the ambient vibration test or the mode shapes from the ambient vibration test can actually look like. And now we have a calibrated model where the frequencies are matching to the experimental response, and we can use this model now for further investigation. But please remember that this is calibrated with respect to the dynamic response, but in a linear domain. So whatever you choose for the nonlinear response later on is something which is very uncertain and must be done over a subset of the user choices, must not be done with one particular set of material properties that can be very uncertain and unreliable. Now, in this case, the structure is located here at the bottom of the map, where the peak ground acceleration is around 0.3 d. We run a response spectrum analysis using the complete quadratic combination, and we get as an output, in this case, for example, the stresses, the principal stresses, and the shear stresses. Now, the principal stresses in the total strain-based crack model are typically enough to determine the orientation or the cracking pattern of the structure. But because masonry walls are oriented in a particular direction along the length of the wall, then you are sometimes, or most of the time, you are also interested in looking at the in-plane shear stresses, for example. And the global shear stresses from the model helps us somehow analyze that in a rather simpler, but in a very informative way. In this case, what you see is if you take the material tensile strength limit and you divide it by a confidence factor based on the knowledge level that you have, then you get a limiting value which can be used as a representation of the elastic tensile strength limit of the material. And if you use that value on the legend, then you can see the points which are going into the red color, for example, in this case, are the points which are going beyond the elastic stress range. And these are the points which you must focus on if you want to derive, for example, retrofitting measures, or if you want to derive the strengthening measures for the structural system. The in-plane stresses, depending on the orientation of the wall, that's why you see I have two here, and I'm talking about, for example, shear stresses in XZ plane for this case and in a YZ plane for this case. That's why you see here the shear stresses are oriented in the walls, which is in an in-plane direction to the direction of motion, and here the in-plane direction is this direction. That's why you would see that there is diagonal cracking, for example, from the corner of the opening, or where the facade is large and big, you see that there is a propagation of the crack, although the propagation is over a large part of the wall, because the mesh is not refined enough to capture the actual crack. But in a global analysis and in a very preliminary analysis where you want to identify just the regions of stress concentration, this is enough to understand the structural response in a rather preliminary and global way. But if we go into the nonlinear analysis, then I will show you another case studies where we have more detailed results and where we have we go a little beyond the stresses to understand the structural response. Now, the Trakošćan Castle was built in the late 13th century as a defense fortress, and then it was later abandoned, restored in the 19th century, and then nationalized after World War II. And it is now a cultural heritage site, protected cultural heritage site, the UNESCO World Heritage List. The structure was damaged in 1982, where there was cracking in the tower, and the floor of the structural system was damaged. The seismic hazard map assigns a PGO of 0.18 G for the 475 years for the Trakošćan site, and this is what we will use as information for the time history analysis. Now, in this case, the structure is again stone and brick masonry in lime mortar. The non-structural roof and timber floor have variable beam depths of between 18 and 25 centimeters. We again have a vaulted system in the floor. This is the external vault that you will see later in the structural model on this side between the two artillery towers. The geometry is very irregular, and the load path is rather very complex because the base of the structure is not located on a single elevation level. Now, the material properties that we take for stone masonry, stone and brick masonry in lime mortar, we take it from the region, from a book. Here, we take it from the region, and you would see there is always a range of material property that we can play with. And because the building was constructed over a period of time, and not in 1 year, over a period of time, that means that the building material is not consistent. So we must assign two different parts of the structural system depending on the plan and from the available data on which year what part was constructed. And we assign a different material property to different structural system, but this gives rise to another problem. Now, when we are calibrating the numerical model, we must change each of these set of material in a particular range to determine a set of material that represents the overall structural response, because in the frequencies that we observe from ambient vibration testing, we cannot differentiate between different material properties. So the choice the user have to make, or the sacrifice that the user have to make now, is on calibrating more than one material properties, where it was only one material that was assigned to the whole building in the previous case. Now again, we use the total strain-based crack model. The crack orientation is again rotating. In this case, the tensile law is exponential and the compressive law is parabolic, but this is again only one set of results. Now, you would see in this case, the mesh is more complex. It is not consistent. The neither the size nor the shape of the element is consistent. You would see the columns connected to the wall where the mesh is very refined, and this is done automatically by the powerful mesher that the software has. Now, in this case, the frequencies were not observed in one time. Rather, the frequencies were observed in 2016, which you see here as the light color lines. And then the frequencies were observed after the Zagreb and Petrinja earthquake in 2021. And you would see between the line and the dark columns, the frequencies have slightly decreased, which means the period has elongated. And this can only indicate that because of these earthquakes, there's been a damage in the structural system. And this is good information to construct a model with the frequencies in 2016 and then construct a model with the frequencies in 2021 to understand where the structural damages could have been to cause the shift of period from 2016 to 2021. In this case, the ambient vibration testing is carried out here in the tower, here in the second floor, and here in the second floor. Then we change the material properties, we look at the error, we minimize the error, and then after minimizing the error, we look at the response of the structure, and we see that we can identify the frequency of the first mode shape, which is around 2.54 Hertz in the north-south direction. The north-south direction is here, the tower frequencies are here, and you would see here it is around 2.8. Here we have 2.54. A perfect match is most of the time never possible because with large structures and with heavy masses, it is not really possible most of the time to calibrate the model in a way where the dynamic response is 100% captured in all directions. That's why we make a sacrifice always by looking at the error and saying that, okay, a 10% error or maybe a 15% error is an acceptable error for a particular case study. We also observe the frequencies in the east-west direction, which are now here. The frequency for the tower is around 3 Hertz in 2016 and 2.9 Hertz in 2019, but we see here a 2.6 Hertz because it's never a perfect match. And then we also have a global mode shape where not only the tower is moving, but the structure as a whole is moving. And this we get from position 1 and position 2, where the response is not measured on the tower, but on the second floor. Now, in this case, for the nonlinear analysis, the soil type is A, the spectrum type is 1 according to Eurocode 8, the PGA is 0.18 G, and because we do not want to run a time history analysis for different records, that's why, and because we do not have records that are from the particular region, that's why we run a time history analysis by spectrally matching the record that we have from the closest seismic station with the same subsoil conditions and scaling it to the 475 years return period so that we can simulate an earthquake level required by the code. What you see on the right side are the principal tensile stresses, which shows you, and they are instantaneous stresses, so they show you the concentration beyond the elastic limit at every step of the analysis. And you would see that the stresses are mostly concentrated in the walls that are on the outside between the two artillery walls because they are free to move on one end. You would also see a stress concentration here at the base of the tower because this is the tower acts as a cantilever body and there is a large concentration of stresses because of higher deflections in the larger tower or the watchtower. There's also stress concentration on the curved shell paths, but this is something that you would see on the next slide in a more clear way. So here is a comparison of the 95-year return PGA value and the 475-year return PGA value for the particular site. Now, for the 100-year earthquake, the structure is more or less safe, although there are some regions where the stress exceeds the elastic limit, but this does not indicate that the structure has failed. When the elastic limit is exceeded, it only tells you that the part is going into a nonlinear range, but it does not tell you exactly if it has failed or not. So that's something that we never know. So it must be interpreted in a way that we can see the concentration of stresses as an indicator of the load path, or an indicator of where our focus should be, rather than indicating if the part has failed or not. Now, for 475 years, this structure will have very heavy damages, or expectedly very heavy damages, and will probably not sustain a 475 years earthquake. Now, from the in-plane shear stresses, you see the orientation of the stresses depends on what we are looking, or which component of stress we are looking at. And you would see for the 100-year earthquake, the stresses are mostly located on the areas which are close to the tower, which is understandable because of the crack opening due to the tensile loss of strength. The shear stresses are also formed, or the shear stress retention. There is a shear concentration in these parts closer to the tower. And this is understandable because you would expect this because of the formation of cracks at the base of the tower, both in tensile and shear manner. But there is also stress concentration in the corners of the walls or near the openings, where you also expect them in the in-plane direction because of the irregularity that the opening brings to the distribution of forces in the facade. Now, we can also look to the vaults or the vaulted structures, and we would see that the edges of the vaults are the parts which are typically more vulnerable. And the reason is because either the support length for the vault is too small, although we are assuming a perfect connection between the vault and the wall, but still, if there is not enough support length on the wall for the vaults, these are the areas that we should be concerned about when retrofitting the structure later on, or when the structure is remodeled. For example, when the connections are known, then these are the parts which should be modeled with more clarity. Now, the stresses gives you a good understanding of the concentration, but if you are interested, for example, in the orientation of the cracks, then maybe the strain is the correct information that you should be looking at. Between the stresses and the strains, you can see the strains provide a much better, clearer picture. For example, you can see a crack that originates from the opening and moves toward the top of the artillery tower. Here, you also see a stress concentration, but you cannot see the path of the stresses. So the strain in this case gives you a better overview of the orientation of the cracks, or the orientation of the concentration in a particular direction. Now, you can also look to the shear strain, where you can see the diagonal cracking, for example, but you cannot compare it to a number to understand if this should be interpreted as a failure or not. Now, in the whole results, these can only be interpreted as preliminary results, but this is enough for a preliminary investigation to understand if the structure would globally be able to resist a particular level of seismic excitation. When you are interested in a more detailed analysis, then we build localized models out of a bigger model, because then it is easy to refine the mesh, and it is easy to make the connections or define the connections as interface elements, derive more detailed analysis of a particular part of the structural system. So a sub-level model would allow a better representation of the crack pattern, but a global level model only helps you understand the structural response on a global way without going into the details of how a crack propagates, or how if the cracks are shear cracks or tensile cracks in a very detailed, sophisticated manner. Now, in summary, our built heritage is always at risk due to natural or man-made hazards, and particularly earthquakes. So the effective seismic performance evaluation and risk assessment is always crucial. The individuality of each cultural heritage building demands always a thorough understanding of the structural response before you can decide on any intervention measure. That means that every cultural heritage building is unique, and it should be addressed in a unique manner. The analysis often needs a balance between the level of detail that you can define and the availability of resources, including time and data. The nonlinear material modeling, it always requires an extensive amount of data, and this is often which is not readily available to us. And sometimes we are not able to obtain these from experiments because of the cultural heritage aspects of these buildings. This brings uncertainties, and this also brings large differences in the predictions. And then this also limits us to make either a global or a local assessment, depending on the level of availability of data that we have. Now, Diana in general, it offers a very good, I would say, a range of material models that can be used for or adopted for the analysis of masonry and cultural heritage buildings. For example, the total strain-based crack model for solid elements, or the engineering masonry model if you are using the shell element, and sometimes the Rankine hill will be also used, but probably in older models and not really in the newer ones. Now, this brings me to the point where I would like to thank Diana for the invitation to the technical webinar, and to my professors for constantly supporting and encouraging me. This was a part, or these analyses are a part of a prior project, which was supported by the Croatian Science Foundation, and this is a part of my PhD. So I would thank you for your attention, and I would now take questions if you have any.
Thank you very much, Anis, for this very nice and very comprehensive presentation, and for the nice work that has been done. That's a very interesting one. And apologize, Weimar is indeed in Germany. I was thinking about Vienna in Australia, so my mistake. I apologize for that, Anis. There is a question. I'm going to raise this question to you, and yeah, feel free to answer it if you can. How the frequencies that are being recorded in situ are produced and recorded?
So the process of recording frequencies in the site is called ambient vibration testing. This is a particularly this method particularly is called HTSR, or horizontal to vertical spectral ratio, and it is typically employed for geotechnical applications. So you take an accelerometer, you put it on the site, and you are monitoring the response or the accelerations without any excitation. So these instruments, or HPSR instruments, are typically able to capture small vibrations without any excitation. So you are relying on ambient vibrations that can arise from movement of people, or from car passing nearby, or things like that. So you don't need an active excitation system. Rather, you are relying on the small vibrations that we always have in the structural system. You cannot feel them, but they are always there. And once you have these vibrations, then you can create a Fourier response spectrum out of the time history of vibrations. And this Fourier response spectrum, where the peak is, the peak gives you information about where the fundamental frequencies of the structural system are. I hope that answers your question.
I think you answered actually even the second question, because the second question was if the natural vibrations would impact the recording, or it's not a concern.
So the natural vibrations are the source of excitation in this case. Yeah. So because there is no active excitation, we are relying on the natural vibrations as the source of excitation, because if you excite the structure, then you have a forced vibration system, and then it becomes even difficult to compare to the eigenvalue or a free vibration analysis.
Yeah, thank you for the answer, Anis. There are a few other questions that are very much related to Diana features. So these are questions that I would be more than happy to answer per email, because they can point to some part of our online documentation. For the rest, it's mainly compliment for your presentation. So on behalf of the audience, let me again thank you for this very nice presentation, Anis. It was very great to have you as a guest lecturer today. It was very nice, and thank you for your contribution. As I mentioned at the start of the presentation, this webinar has been recorded. In the coming days, Anis is going to review this recording session, and if everything is fine, then we will publish it on our YouTube channel. So probably early next week, the video will be available on our YouTube channel. So keep an eye on this channel, and also keep an eye on our website. There are more events planned in terms of webinars and also courses. So please do not hesitate to register to our newsletter if you want to be informed about the latest development on our site. So I think we can conclude this webinar for today. And again, on behalf of Diana and on behalf of the large audience that we had today, I'd like to thank you one more time, Anaïs, for taking the time to present your work, and with some Diana flavor, which is always nice. It was a great presentation, very comprehensive, and yeah, there is a lot of compliment about that. So I want to share that with you. So thanks a lot, Anaïs. Maybe you want to have a last word for the audience.
Thank you very much. Thank you for listening to me, and I am of course always available on my email. So if you have any questions or any discussions, please feel free to write me an email.
Yeah, and you can also send the questions to me, and if they are really on the topic, I will be more than happy to share them with Anaïs. So you can always reach us. I mean, questions are always welcome. So thank you all for this for attending this webinar, and yeah, we probably see each other in the next webinar, which is planned early December. So thank you all. Have a nice day, and yeah, don't miss the news on our website. Just register on the newsletter. Thank you. Bye.